Welcome to another deep dive. Sometimes in science, you come across figures whose work is so fundamental, it's almost like they rewrote the rules of the game.
Yeah.
And today, we're tackling one of those giants. We're going to explore the life and work of Emmy Noether.
Oh, fantastic choice. Emmy Noether is truly a legend, especially in the realms of mathematics and theoretical physics.
Right. And for this deep dive, we're going to be guided by a really insightful essay from Jorgo Schneeppat. It does a fantastic job of capturing her genius and the impact she had.
Absolutely. Schneeppat really nails it. You think about it. Noether was born in 1882.
Right.
A time when, well, let's be honest, the world of science was pretty much a boys' club.
100%.
But she wasn't just content with playing by the rules. She smashed those barriers and delivered some of the most profound insights into how the universe works.
It's mind-blowing when you think about what she accomplished. Her most famous contribution, Noether's Theorem, is this incredible link between symmetry in physical systems and conservation laws. And Schneeppat does a great job of explaining it in a way that even I could grasp.
Yeah, it's one of those things that once you understand it, it just makes you go, whoa, how did we not see this before?
Totally. So today our mission is to unpack Noether's story, understand her profound impact on both mathematics and physics, and explore why her work remains so vitally important today. It's like a journey into the fundamental laws of the universe.
And I think what's really cool is that her story goes way beyond just equations and theorems. It's also a story about perseverance, breaking down barriers, and the sheer power of a brilliant mind.
Absolutely. So let's dive into Emmy Noether's world, starting with her early life and education. Schneeppat mentions that she was born into a family that was pretty steeped in academia, especially mathematics. Her father, Max Noether, was a prominent mathematician himself.
Yeah, that definitely played a role. Imagine growing up with a mathematician as your dad. I'm sure dinner table conversations were a bit different.
I bet. But even with that background, Schneeppat points out that accessing higher education as a woman in Germany back then was like trying to climb Mount Everest in flip-flops. It was a serious uphill battle.
Oh, absolutely. The societal norms were incredibly rigid. Women were basically expected to become teachers or housewives, not groundbreaking mathematicians.
It's wild to think about, and Schneeppat highlights that initially, Noether actually focused on languages, studying French and English. These were seen as acceptable subjects for women, but that burning passion for math just wouldn't quit.
It's almost like you can see that spark in her, even from a young age, this drive to explore the abstract world of numbers and patterns.
Totally. And around 1900, she managed to get permission to audit university courses, which was a huge step, but still not the full deal. Can you imagine the dedication, sitting in on these advanced lectures without officially being a student?
Yeah, that takes serious commitment. It really shows how much she wanted it.
It does. And then finally, in 1903, the rules relaxed just enough for her to formally enroll as a math student. But even then, Schneeppat makes it clear that it was far from a level playing field. She was constantly navigating this male-dominated environment.
It's hard to overstate the challenges she must have faced. Imagine being the only woman in the room, constantly having to prove yourself.
Must have been exhausting. But Noether persevered. She earned her doctorate in 1907 under the supervision of Paul Gordon, another big name in mathematics. Her dissertation, as Schneeppat explains, focused on algebraic invariants. Now, for those of us who aren't math whizzes, what exactly are algebraic invariants?
So think of it this way. Invariants are kind of like the unshakable truths of mathematics.
Okay, so something that stays constant.
Exactly.
Yeah.
No matter how you transform certain variables, these invariant expressions hold their value. It's like finding the bedrock in a sea of changing numbers. And what's really interesting is that Noether's early work, particularly her focus on something called symmetric invariance, was kind of a preview of her later groundbreaking discoveries. It's like the seeds of her future work were planted right there.
That's so cool. It's like those early experiences were shaping her thinking in ways she might not have even realized at the time.
Yeah, I love those little connections in a person's intellectual journey.
Me too. So she's got her doctorate. This brilliant mind is firing on all cylinders. What happens next in her academic career?
Well, sadly, as Schneeppat details, the academic world wasn't quite ready to embrace a female genius just yet.
Some more hurdles?
More like brick walls. Because of her gender, she couldn't secure a proper academic position. Imagine that.
It's mind-boggling.
So initially, she ended up working with her father, supporting his teaching and research. Schneeppat even mentions that there's evidence she sometimes published under his name. Think about the frustration.
The injustice is just staggering. It's like having this incredible gift and being told you can't share it with the world under your own name.
Yeah, a real tragedy. But even in these difficult circumstances, her brilliance couldn't be hidden forever.
And this is where Schneeppert talks about her move to Göttingen in 1915, right?
Exactly. That move was a pivotal moment. Göttingen was, and still is, this world-renowned center for mathematics and physics.
A real hub of intellectual activity.
And it was there that she started collaborating with some of the biggest names in the field, people like David Hilbert and Felix Klein.
These are legends.
Absolute giants. And Hilbert, in particular, immediately saw Noether's genius. He became a huge champion of her work, pushing for her to have a proper position at the university.
Schneeppert mentions this amazing quote from Hilbert when he was fighting for Noether's appointment. He basically said to the university senate, "My lords, the senate is not a bathhouse. Why should the sex of a candidate be a reason to refuse their habilitation?"
I love that quote.
Right. It so perfectly captures the absurdity of the prejudice she faced.
100%. Here's this brilliant mind revolutionizing mathematics, and they're worried about what?
It's just ridiculous.
Sadly, even with Hilbert's support, it still took until 1919 for Noether to finally secure a lectureship. And get this, it was unpaid.
Unbelievable.
But it was during this period, in 1918, that she formulated her most famous contribution, Noether's Theorem. This is the big one, the one that really changed the game.
So can we dive into that a bit? What makes Noether's theorem so revolutionary? What's the key insight?
Okay, so in a nutshell, Noether's theorem establishes this beautiful connection between symmetry in physical systems and what we call conservation laws.
Okay, break that down for me. What do we mean by symmetry in a physical system?
Think of it this way. A symmetry is any transformation you can do to a system that doesn't change the underlying physics. So imagine you have a ball rolling on a perfectly smooth surface.
Okay, got it.
Now, if you slide that entire setup to the left or right, the ball will still roll in the same way, right?
Makes sense.
That's spatial translation symmetry. The laws of motion don't care where the system is located in space. It's the same physics.
I'm following.
Noether's theorem basically says that whenever you have a symmetry like that, there's a corresponding physical quantity that must be conserved. So in the case of spatial translation symmetry, the conserved quantity is momentum.
So because the system behaves the same regardless of its position in space, momentum has to be conserved.
Exactly. It's like the universe is keeping a balance sheet.
I like that analogy.
And Schneeppert gives some other great examples.
Yeah.
Time translation symmetry means the laws of physics are the same today as they were yesterday. And the corresponding conserved quantity there is energy.
Ah, that's why energy can't be created or destroyed, only transformed from one form to another.
Precisely. And then there's rotational symmetry. Spin atop, and the physics governing its motion stays the same. That leads to the conservation of angular momentum.
Wow, so it's all connected. These fundamental symmetries are directly tied to the conservation laws that underpin so much of physics.
It's like Noether gave us this secret code to unlock the universe's inner workings.
It's so elegant. Schneeppert mentions that Noether's theorem has a formal mathematical expression within the framework of something called Lagrangian mechanics. Can you give us a simplified explanation of that?
Sure. In Lagrangian mechanics, you describe a physical system using something called the Lagrangian, which basically encapsulates the system's energy. And what Noether figured out is that if you make a transformation that corresponds to a symmetry, meaning it leaves the Lagrangian unchanged, then you automatically get a conservation law.
So if the recipe for the system's energy stays the same, some ingredient in that recipe must remain constant?
That's a great way to put it. And the amazing thing is that Noether's theorem applies not just to classical physics, like balls rolling and planets orbiting, but also to the weird and wonderful world of quantum mechanics.
So from the macroscopic to the microscopic, these connections between symmetry and conservation laws hold true. That's pretty mind-blowing.
Right. And as Schneeppert points out, Noether's theorem has particularly deep implications for quantum mechanics and something called quantum field theory, which is basically the language we use to describe fundamental particles and forces.
Now that's getting into some pretty heavy stuff. Can you break down why it's so crucial in those areas?
Absolutely. In quantum field theory, instead of dealing with individual particles, you describe everything in terms of fields, which are sort of like properties that exist throughout space and time. Imagine the electromagnetic field, for example.
Okay, got it.
And it turns out that Noether's theorem helps us connect symmetries in these fields to the conservation of incredibly important quantities. For example, Lorentz invariance, which is basically the idea that the laws of physics are the same regardless of your speed or orientation, leads directly to the conservation of energy and momentum.
Oh, wow.
And another type of symmetry, called U1 gauge symmetry, is directly linked to the conservation of electric charge. These are bedrock principles that underpin our understanding of the universe.
So Noether's theorem is literally woven into the fabric of reality. It's not just some abstract mathematical curiosity.
It's the real deal. And Schneeppert also highlights how it connects to another cornerstone of quantum mechanics, the Schrödinger equation. The one that describes how quantum systems evolve over time.
Vaguely.
What's fascinating is that the Schrödinger equation is deeply rooted in symmetry principles. And Noether's theorem kind of provides the mathematical justification for this.
So, it explains why the equation works the way it does.
Exactly. It's like she revealed this hidden architecture within the mathematics of quantum mechanics. And within the Schrödinger equation, there are these things called operators, which represent physical quantities like energy, momentum, and angular momentum.
Right.
And it turns out that these operators are directly linked to symmetry operations. Time translation symmetry gives you the Hamiltonian operator, which represents energy. Space translation symmetry gives you the momentum operator, and so on.
It's all coming together. It's like this beautiful tapestry of interconnected ideas.
That's a great way to put it. And Schneeppert goes on to talk about how Noether's work has been further developed and applied by countless physicists over the years, especially in areas like quantum field theory and even in attempts to unify gravity with the other forces.
So her impact continues to ripple outward.
Absolutely. And Schneeppert makes a particularly interesting point about the standard model of particle physics. This is like our best current theory of the fundamental particles and forces that make up the universe. And at the heart of the standard model are these things called gauge symmetries, which are essentially rules about how different parts of the theory can be transformed without changing the overall physics.
Okay.
And guess what? Noether's theorem is crucial for understanding how these gauge symmetries lead to the conservation laws we observe, things like the conservation of electric charge, baryon number, and lepton number.
So it's like Noether's work provided the blueprint for understanding these fundamental building blocks of reality.
It's truly foundational. And it's not just particle physics. Schneeppert even mentions that her work has implications for cutting-edge theories, like string theory, which tries to unify all the forces of nature, including gravity.
So from the smallest subatomic particles to the very fabric of space-time, Noether's theorem is at play.
It's everywhere. And Schneeppert doesn't stop there. He also dives into the more practical side of things, talking about the impact of Noether's work on quantum science and technology, particularly in areas like quantum computing.
Oh, so this really abstract stuff has tangible applications.
Absolutely. Think about it. Noether's theorem is all about connecting symmetries to conserved quantities. And in quantum computing, one of the biggest challenges is figuring out how to protect fragile quantum information from errors. And it turns out that a lot of the techniques we use for this, like quantum error correction codes, rely heavily on principles of symmetry.
So the work she did almost a century ago is helping us build the technologies of the future.
It's amazing, right? And it's not just quantum computing. Schneeppert also points out that symmetries are crucial in understanding how quantum systems behave and in designing new quantum algorithms, like those used for searching databases or factoring large numbers.
So her impact is truly far-reaching. But beyond her scientific contributions, Schneeppert also highlights the importance of Emmy Noether as a role model, especially for women in science. I mean, her story is incredibly inspiring given all the obstacles she had to overcome.
Yeah, no kidding. She was fighting an uphill battle every step of the way. Imagine being told you can't do something simply because of your gender. It's infuriating.
Totally. And yet, she persisted. She achieved incredible things in a world that was actively trying to hold her back.
Exactly. And her story is still so relevant today. We're still battling systemic biases and inequalities in science. And Noah's legacy reminds us that we have so much to gain by embracing diversity and giving everyone a chance to contribute.
100%. Schneeppert also talks about her exile from Germany in the 1930s due to the rise of the Nazi regime. She ended up in the United States, where she continued to make significant contributions at Bryn Mawr College and the Institute for Advanced Study.
Right, another reminder of the importance of welcoming scientific talent from around the world. We all benefit when we break down those barriers.
Absolutely. And it's great to see that, even though it took far too long, Noether's contributions have received more and more recognition over the years.
It's about time. Schneeppert mentions things like the Emmy Noether Prize, named in her honor, and the fact that her work is now taught in universities all over the world. It's becoming increasingly clear that she was one of the most influential figures in 20th century science.
A true titan. And Schneeppert does a great job of bringing it all together in his conclusion. He really drives home the point that Emmy Noether's legacy goes way beyond just a bunch of equations. It's about the power of a brilliant mind to change the way we see the universe, to push boundaries, and to inspire future generations.
Yeah, her story is a reminder that scientific progress relies on those individuals who are willing to challenge conventions, ask bold questions, and, as Noether did so brilliantly, reveal the hidden connections that underpin the world around us.
It's a powerful message, and as we wrap up this deep dive, guided by the insights of Jorgo Schneppe, I think it's worth taking a moment to just marvel at the sheer ingenuity of Emmy Noether.
Absolutely. And maybe even consider this. What other hidden connections might be out there, just waiting to be discovered by those who dare to look beyond the surface and explore the universe with the same curiosity and intellectual rigor that Emmy Noether embodied?
It's a question worth pondering. Thanks for joining me on this deep dive, and a huge thank you to Jorgo Schneppe for his insightful essay.
It's been a pleasure. Until next time.